No, really, just imagine closing your eyes right now. What do you see? You probably think you see darkness, right? That inky black void behind your eyelids that feels like nothingness. But here is the thing, and this is going to bother you for the rest of this video. What you see when you close your eyes is not darkness, not even close. Your brain is actually generating a colour, a specific shade of dark grey that scientists call Eigengrau, which literally translates from German as intrinsic grey. Your retinal cells are still firing, still sending signals, still creating a visual experience even when no light is entering your eyes. You have never, not once in your entire life, experienced true darkness. Not when you turned off all the lights in your room, not when you buried your face in your pillow at 3 a.m, not even in the deepest, darkest cave you could possibly find on this planet. Every single environment you have ever been in has had photons, particles of light bouncing around, hitting your retina, giving your brain something to work with. But out there in the vast stretches between the stars, in the yawning gulfs between galaxies, in the incomprehensible emptiness that makes up most of the universe, there exists a darkness so absolute, so profound, so fundamentally different from anything you have ever experienced that your brain literally does not have the hardware to process it. And today, we are going to journey into that darkness. We are going to ask questions that kept the greatest minds in human history awake at night. We are going to confront truths about our universe that are equal parts beautiful and terrifying. And by the end of this video, I promise you, you will never look at the night sky the same way again. So what exactly are we going to explore today? Let me give you a taste. Why is space dark? I know that sounds like a simple question, maybe even a childish one, something a 5-year-old might ask while looking up at the stars. But this seemingly innocent question tormented physicists, astronomers, and philosophers for over 400 years. 4 centuries of the greatest human minds wrestling with a puzzle that seemed to have no solution. Because here is the paradox. If the universe is filled with trillions upon trillions of stars, each one a blazing nuclear furnace pouring out light in every direction, then why is the space between them dark? Why isn't the entire sky white hot with starlight? The answer, when it finally came, didn't just solve the puzzle. It revealed something shocking about the very nature of reality itself. It told us that the universe had a beginning. It told us that the universe is expanding. And it told us that everything, every star, every galaxy, every photon of light, is slowly, inexorably sliding toward an eternal darkness that will last forever. But that is just the beginning. We are going to explore what happens to the human mind when it is exposed to true darkness. We are going to visit the darkest places in the known universe, voids so empty, so devoid of light and matter, that they challenge our very understanding of how the cosmos is structured. We are going to dive into black holes, objects so dark that they represent the literal end of light, places where photons go in and never come out. We are going to confront the staggering fact that 95% of the universe is made of stuff we cannot see, stuff we call dark matter and dark energy, and despite decades of searching, we have almost no idea what they actually are. And we are going to peer into the future, into the ultimate fate of the cosmos, and discover that the darkness we see today is nothing, absolutely nothing, compared to the darkness that is coming. This is going to be a long journey, a deep journey, a journey that spans the entire history and future of the universe. So if you are someone who loves exploring the deepest mysteries of the cosmos, if you are someone who wants to understand not just what we know, but what we don't know, if you are someone who finds beauty in the terrifying vastness of space, then do me a favor right now. Hit that subscribe button. Press the bell icon so you never miss a video like this. Because today, we are going deeper than we have ever gone before. And I mean that literally and figuratively. Let us begin with something that might seem obvious, but is actually deeply strange. What is darkness? I mean, what is it really, at a fundamental physical level? We use the word so casually. We say the room is dark, the night is dark, space is dark. but we rarely stop to think about what we actually mean. In physics, darkness is simply the absence of photons. Photons are the fundamental particles of light, the carriers of electromagnetic radiation. When photons hit the photoreceptor cells in your retina, the rods and cones, they trigger chemical reactions that send electrical signals to your brain. Your brain interprets these signals as light and color. When no photons are hitting your retina, you should experience darkness. But here is where it gets interesting. On Earth, you are never in a situation where 0 photons are reaching your eyes. Never. Even in what you think is total darkness, there are photons everywhere. The walls of your room are emitting infrared photons because they have a temperature above absolute 0. Cosmic rays from deep space are passing through your house and occasionally generating faint flickers of Cherenkov radiation. The electrical activity in your own retinal cells is producing random signals that your brain interprets as faint spots of light, those little squiggles and dots you see when you close your eyes in a dark room. Even in the most carefully constructed dark rooms in scientific laboratories, rooms designed to block out every possible source of light, there are still stray photons leaking in, still thermal radiation from the walls, still the quantum noise of the vacuum itself producing virtual photon pairs that flicker in and out of existence on timescales too small to measure. So here is a question that should make you a little uncomfortable. If you have never experienced true darkness, how do you know what it is? How can you possibly understand the darkness of deep space if you have no reference point, no experience, no sensory framework for something so fundamentally alien to your biology? The answer is, you can't. Not really. You can only approximate it in your imagination, and even then, your imagination is limited by your experience. But let us try anyway, because the attempt to understand is where the beauty lies. Imagine you are an astronaut, not on the International Space Station, which orbits just 400 kilometers above Earth's surface, close enough to see city lights at night and the brilliant blue of the atmosphere during the day. No. Imagine you are much farther out. Imagine you are on a spacecraft traveling through the interstellar medium, the space between stars. Your ship's engines have shut down. Your lights have gone out. Every system is dark. You float to a window and look out. What do you see? Well, you see stars. Thousands of them. Millions of them. Pinpricks of light scattered across the velvet blackness in every direction. That might not sound so bad. It might even sound beautiful. And it is. But here is what most people don't realize. Those stars, as numerous as they appear, illuminate almost nothing. The light from even the closest star to our sun, Proxima Centauri, which is about 4.2 light-years away, is so faint by the time it reaches you that it provides less illumination than a single candle placed on the moon would provide to someone standing on Earth. The starlight you see is not illuminating the space around it. Each star is a tiny, isolated beacon in an ocean of darkness so vast that the light simply gets swallowed up, diluted, rendered meaningless by the sheer incomprehensible volume of empty space. If you turned away from the window and looked at your own hand, you would not be able to see it. The combined light of every visible star in the sky is not enough to let you see your own fingers in front of your face. That is how dark interstellar space is. But we are not done going deeper. Let us push farther out. Let us leave the Milky Way entirely and travel into intergalactic space. Now you are not between stars, you are between galaxies. The nearest major galaxy, the Andromeda Galaxy, is 2.5 million light-years away. To put that in perspective, light, the fastest thing in the universe, travelling at 300,000 kilometers per second, takes 2.5 million years to cross that gap, and between you and Andromeda, there is essentially nothing. A few stray hydrogen atoms per cubic meter. Maybe the occasional rogue star ejected from its home galaxy by gravitational interactions, wandering alone in the darkness forever. But mostly nothing. The darkness here is deeper, more complete, more oppressive than anything in interstellar space. The Milky Way behind you is no longer a river of stars across the sky. It is a faint fuzzy smudge, a pale oval of diffuse light. And even that light is providing essentially zero illumination to your surroundings. You are floating in a void so absolute that the word dark doesn't begin to describe it. But even this is not the darkest it gets. Let us go to one of the great cosmic voids. Let us go to the Boots Void. This is a region of space, approximately 330 million light-years in diameter. To put that in context, our entire Milky Way galaxy is about 100,000 light-years across. The Boots Void could contain thousands of galaxies, and indeed it should contain thousands of galaxies based on the average density of the universe. But it doesn't. It contains only about 60 galaxies scattered through this immense volume of nothingness. 60 galaxies in a region where you would expect 2,000 or more. If Earth were located at the center of the Boots Void, we would have had no idea that other galaxies existed until the 1960s, when our telescopes finally became powerful enough to detect the faint, distant galaxies at the void's edges. For most of human history, we would have looked up at the night sky and seen only our own galaxy, alone, isolated, a single island of light in what appeared to be an infinite, featureless darkness. We would have had no reason to suspect that the universe extended beyond our galaxy. We might have concluded that our galaxy was the entire universe. Think about how fundamentally that would have changed our understanding of everything. All of cosmology, all of our knowledge about the Big Bang, the expansion of the universe, the cosmic web, all of it depends on being able to observe other galaxies. In the Boots Void, most of that knowledge would be inaccessible. The darkness would not just be physical, it would be intellectual. It would be a darkness of ignorance imposed by the darkness of space. Now I want you to hold that thought, that image of the Boots Void, that feeling of cosmic isolation, because we are going to come back to it later in a context that will make it even more unsettling. For now, let us rewind. Let us go back to the question that started all of this, the question that haunted astronomers for 400 years. Why is the night sky dark? This question has a name. It is called Olbers Paradox, named after the German astronomer Heinrich Wilhelm Olbers, who formalized it in 1823. But Olbers was far from the first person to think about it. The roots of this paradox go back much farther, and the story of how humanity struggled with this question is one of the most fascinating chapters in the history of science. Let us set the stage. For most of human history, people didn't need to worry about why the sky is dark at night. The ancient model of the cosmos was relatively simple. Earth was at the center, surrounded by crystalline spheres carrying the moon, the sun, the planets, and the stars. The stars were fixed to the outermost sphere, and beyond that sphere was either nothing or the realm of the divine, depending on your philosophical and religious tradition. In this model, there was a finite number of stars on a finite sphere. The sky was dark at night because there were gaps between the stars. Simple as that. No paradox, no problem. But then came the Copernican revolution. Nicholas Copernicus proposed in 1543 that Earth was not the center of the universe, that Earth orbited the Sun just like the other planets. This was revolutionary enough on its own, but its implications went much further than Copernicus himself realized. If Earth was not at the center, if the Sun was just another star, then maybe the stars were not fixed to a crystal sphere. Maybe they were other suns, scattered through space at various distances. And if space was infinite, then there might be an infinite number of stars extending in every direction without end. Thomas Digges, an English mathematician and astronomer, was one of the first to take this idea seriously. In 1576, he published a model of the cosmos in which the stars were not confined to a sphere but were scattered throughout an infinite space. And this is where the trouble began. Because if you have an infinite universe with an infinite number of stars distributed more or less uniformly through space, then a very strange conclusion follows. If you look in any direction, your line of sight should eventually intersect the surface of a star. It might be a nearby star or a star billions of light years away, but eventually, if you follow any line of sight far enough, it must hit a star. This means that every single point in the sky should be as bright as the surface of a star. The entire sky, day and night, should be blazing with light. Not just a little bit of light, but a lot of light. The sky should be roughly as bright as the surface of the sun. Everywhere, in every direction. There should be no darkness at all. Johannes Kepler, the great German astronomer who discovered the laws of planetary motion, recognized this problem around 1610. For Kepler, the dark night sky was evidence that the universe could not be infinite. If the universe had a boundary, if there were only a finite number of stars in a finite volume, then the paradox dissolved. There wouldn't be enough stars to fill every line of sight. Kepler was right about the conclusion, but not entirely right about the reasoning, as we'll see. Over the next 2 centuries, other scientists grappled with the problem. Edmund Halley, the English astronomer famous for predicting the return of Halley's comet, proposed in 1720 that distant stars might be so far away that their light was too faint to see. This sounds reasonable, but it doesn't actually work. Here is why. Imagine the universe divided into concentric shells around Earth, like the layers of an onion. Each shell is a certain distance from us. Now, it is true that individual stars in more distant shells appear fainter, because the brightness of a star decreases with the square of the distance. A star twice as far away appears 4 times fainter. A star 10 times as far away appears 100 times fainter. But here is the catch. The volume of each shell increases with the square of the distance as well. A shell twice as far away contains 4 times as many stars. A shell 10 times as far away contains 100 times as many stars. So the decrease in brightness of individual stars is exactly compensated by the increase in the number of stars. Each shell, regardless of its distance, contributes the same total amount of light to the sky. And if there are infinitely many shells, extending to infinity, then the total light should be infinite. Or at least, it should be enough to make the entire sky as bright as a stellar surface. Halley's solution didn't work. In 1744, the Swiss astronomer Jean-Philippe de Chezeaux gave the paradox a more rigorous mathematical treatment and proposed a different solution. Maybe, he suggested, interstellar space is not perfectly transparent. Maybe there is some kind of absorbing material between the stars that blocks the light from distant sources. This would explain why we don't see the light from the most distant stars, because it gets absorbed along the way. This sounds like a good idea, and it was certainly clever. But it doesn't work either, for a reason that is beautifully simple and physically devastating. If the absorbing material blocks light, it must absorb the energy of that light. And that energy has to go somewhere. The absorbing material would heat up. And as it heated up, it would start to glow with its own light, re-emitting the energy it had absorbed. Given enough time, the absorbing material would reach thermal equilibrium with the radiation field and would itself become as bright as the stars it was blocking. The absorption doesn't eliminate the light, it just delays it. The paradox remains. Heinrich Olbers, in 1823, proposed essentially the same absorption solution that de Chezeaux had suggested, apparently unaware of the earlier work. The paradox became associated with his name, somewhat unfairly to de Chezeaux, and has been known as Olbers' paradox ever since. And despite the flaw in Olbers' own proposed solution, the paradox bearing his name would go on to become one of the most important questions in cosmology. Because the real solution to Olbers' paradox didn't just explain why the sky is dark. It told us something profound about the nature of the universe itself. Now, here is where the story takes an unexpected turn. In 1848, 25 years after Olbers published his paradox, a solution remarkably close to the correct one was proposed not by a physicist, not by an astronomer, not by a mathematician, but by a poet. Edgar Allan Poe, the American author famous for dark, gothic tales of horror and mystery, wrote a prose poem called Eureka, in which he attempted nothing less than a grand explanation of the entire cosmos. In Eureka, Poe argued that the universe was not infinite in age, it had a beginning. And because it had a beginning, there had not been enough time for light from the most distant stars to reach us. The sky was dark because we could only see a finite sphere of stars, determined by the age of the universe and the speed of light. Beyond that sphere was darkness, not because there were no stars, but because their light was still on its way. Poe was not entirely right about the details, but his core insight that the finite age of the universe is a key part of the solution was remarkably prescient. A poet writing about the cosmos in the language of beauty and metaphor stumbled upon a truth that the greatest scientists of his era had missed. There is something deeply beautiful about that, something that speaks to the power of imagination and intuition in the face of the universe's mysteries. But we had to wait nearly a century for the full solution to emerge, and it came from a revolution in our understanding of the universe so profound that it changed everything. In 1929, the American astronomer Edwin Hubble made one of the most important discoveries in the history of science. By observing distant galaxies and measuring the shift in the wavelengths of their light, Hubble discovered that the universe is expanding. Galaxies are moving away from us and from each other, and the farther away a galaxy is, the faster it is receding. This was not because galaxies are flying through space like shrapnel from an explosion. It was because space itself is expanding. The fabric of the universe is stretching, and as it stretches, it carries the galaxies along with it. This discovery had staggering implications. If the universe is expanding now, then in the past it must have been smaller. If you rewind the expansion like running a movie backward, everything converges to a single point, a state of infinite density and temperature. This was the Big Bang, the origin of the universe, approximately 13.8 billion years ago. And this is where Olbers Paradox finally gets solved. The real solution has two parts, both arising from our modern understanding of cosmology. The first part is what Edgar Allan Poe intuited in 1848. The universe is not infinitely old. It is approximately 13.8 billion years old. This means that light has had only a finite amount of time to travel through space. We can only see objects whose light has had enough time to reach us since the Big Bang. This defines the observable universe, a sphere centered on Earth with a radius of about 46.5 billion light-years. Wait, you might say, if the universe is only 13.8 billion years old, shouldn't the radius of the observable universe be 13.8 billion light-years? It would be if the universe were not expanding. But because space has been stretching during the entire time that light has been traveling toward us, the objects that emitted the earliest light we can see are now much farther away than 13.8 billion light-years. They have been carried farther away by the expansion of space. So the observable universe is about 93 billion light-years in diameter. Beyond this sphere there may be more universe, perhaps an infinite amount, but its light has not had time to reach us. This immediately limits the number of stars contributing light to our sky. Instead of an infinite number of shells extending to infinity, we have a finite number of shells extending only to the edge of the observable universe. This reduces the total expected brightness of the sky dramatically. But the finite age of the universe alone doesn't completely solve the paradox. You might think that even within the observable universe, there should be enough stars to fill every line of sight. After all, there are roughly 200 billion galaxies in the observable universe, each containing hundreds of billions of stars. That is on the order of 10 to the 24th power stars, a number so large it is essentially incomprehensible. Surely that should be enough to make the sky bright? This is where the second part of the solution comes in, and it is just as important as the first. The expansion of the universe doesn't just carry galaxies apart, it also stretches the wavelength of the light traveling through expanding space. When the wavelength of light increases, its energy decreases and its frequency shifts toward the red end of the spectrum. This is called cosmological redshift. Light from the most distant galaxies, the ones near the edge of the observable universe, has been stretched so much by the expansion of space that it is no longer visible light at all. It has been redshifted into the infrared, then into the microwave, then into the radio part of the electromagnetic spectrum. We cannot see it with our eyes. The most dramatic example of this is the cosmic microwave background radiation, the oldest light in the universe, which was emitted about 380,000 years after the Big Bang. When this light was first released, it was a brilliant orange glow, visible light with a temperature of about 3000 Kelvin. But over the course of 13.8 billion years, the expansion of the universe has stretched its wavelength by a factor of about 1100. It is now microwave radiation with a temperature of just 2.725 Kelvin, less than 3 degrees above absolute zero. This light fills the entire sky in every direction, but it is completely invisible to our eyes. So the sky is dark for two reasons. First, the universe is not infinitely old, so we can only see a finite number of stars. Second, the light from the most distant objects has been redshifted out of the visible spectrum, so even the light that does exist in every direction is invisible to us. The darkness of the night sky is direct observational proof of two of the most profound facts about our universe. It had a beginning, and it is expanding. Every time you look up at the dark sky between the stars, you are seeing evidence of the Big Bang. You are seeing evidence of cosmic expansion. The darkness is not empty. It is full of information. It is the universe telling you its own story, written in the language of absent light. And I want you to sit with that for a moment, because it is genuinely one of the most beautiful things in all of science. A child's question, "Why is the sky dark at night?" leads directly to the most fundamental truths about the origin and structure of the cosmos. The darkness above you is not a void. It is a message. And it took humanity 400 years to learn how to read it. If that doesn't give you chills, I don't know what will. If you are enjoying this deep dive into the mysteries of the cosmos, take a second to hit the like button. Drop a comment and tell me, had you ever heard of Olbers Paradox before? Did you know that a poet came closer to solving it than the physicists of his era? And if you want more content like this, subscribe and hit the bell, because we are just getting started. The darkness has so much more to tell us. Now I want to take you deeper into something I touched on a moment ago, something that changes everything about how we think about the darkness of space. I said that the cosmic microwave background radiation fills the entire sky in every direction, but is invisible to our eyes. That word, invisible, is the key to unlocking a whole new understanding of cosmic darkness. Because here is the thing. When we say space is dark, what we really mean is that space is dark to us. To our specific eyes, with our specific biology, evolved on this specific planet around this specific star. But our eyes are, to put it bluntly, terrible instruments for observing the universe. We see only a vanishingly small fraction of the electromagnetic spectrum. The electromagnetic spectrum is the full range of all possible wavelengths of light, from the longest radio waves, which can be kilometers in length, to the shortest gamma rays, which have wavelengths smaller than an atomic nucleus. In between, you have microwaves, infrared radiation, visible light, ultraviolet radiation, and X-rays. Visible light, the tiny sliver of this spectrum that our eyes can detect, spans wavelengths from about 380 nanometers, which we see as violet, to about 700 nanometers, which we see as red. That is a range of just 320 nanometers out of a spectrum that spans more than 20 orders of magnitude. If the entire electromagnetic spectrum were a piano keyboard stretching from New York to Los Angeles, the visible light portion would be a single key somewhere in the middle of Kansas. This means that when we look at the night sky with our naked eyes and see darkness between the stars, We are making a judgment based on an absurdly limited sample of the available information. It is like listening to a symphony through a wall so thick that you can only hear one note out of a million, and then concluding that the concert hall is silent. If we could see the full electromagnetic spectrum, space would look completely and utterly different. Let us take a tour. Start with radio waves, the longest wavelength of electromagnetic radiation. If your eyes could see radio waves, the sky would be anything but dark. You would see bright spots and streaks everywhere, the signatures of pulsars, rapidly spinning neutron stars that emit beams of radio waves like cosmic lighthouses, sweeping across the sky as they rotate. You would see the lobes of radio galaxies, enormous jets of material blasting out from supermassive black holes at the centers of distant galaxies, extending millions of light years into space, glowing fiercely in radio wavelengths. You would see the subtle, diffuse glow of synchrotron radiation, emitted by electrons spiraling through the magnetic fields that thread through our galaxy. The Milky Way itself would look different, a bright band of radio emissions stretching across the sky, with bright knots marking regions of intense activity. The sky in radio waves is alive, dynamic, anything but dark. Move to shorter wavelengths and you enter the microwave regime. Here, the sky is dominated by something astonishing. The cosmic microwave background, that ancient light from the dawn of time that I mentioned earlier, fills the entire sky with a nearly uniform glow. If your eyes could see microwaves, you would not see a dark sky with a few bright spots. You would see a sky that glows in every direction, every single direction, with almost exactly the same brightness. It would be like being inside a very faint but perfectly uniform light bulb. There would be no dark patches, no gaps, no voids, just a soft, omnipresent glow. And if you looked very, very carefully, you would notice tiny variations in the brightness, fluctuations of about 1 part in 100,000, slightly warmer patches and slightly cooler patches. These infinitesimal ripples are the oldest structures in the universe, the primordial density variations that eventually grew, through the relentless pull of gravity over billions of years, into the galaxies, galaxy clusters, and cosmic web that we see today. Everything in the universe, every star, every planet, every living thing, traces its origin to these faint temperature fluctuations in the microwave sky. You are looking at the seed of your own existence. Move to shorter wavelengths still, and you enter the infrared. This is where hidden treasures emerge. Our universe is filled with dust, tiny grains of silicate and carbon floating in the vast clouds of gas between the stars. This dust blocks visible light, which is why there are dark patches and lanes visible in photographs of the Milky Way. Those dark patches are not empty. They are clouds of dust blocking the light from the stars behind them. But in the infrared, dust is no longer an obstacle. Infrared light passes through dust clouds like sunlight passes through a thin curtain. If you could see in the infrared, those dark patches in the Milky Way would vanish. You would see through them to the billions of stars beyond. The center of our galaxy, which is hidden from us in visible light by thick clouds of dust, would be revealed in all its glory. A dense, brilliant swarm of stars surrounding the supermassive black hole at the heart of the Milky Way. You would also see the thermal glow of the dust itself, warmed by the stars embedded within it, shining softly in the infrared like embers in a cosmic fire. And you would see distant galaxies that are invisible in visible light, galaxies so far away that their light has been redshifted into the infrared by the expansion of the universe. In the infrared sky, the universe is richer, deeper, more populated than it appears to our eyes. Now let us go to the other end of the spectrum, beyond visible light, into the ultraviolet. Here, the sky is dominated by the hottest, most energetic stars, the young, massive blue giants that burn through their nuclear fuel in just a few million years. These stars pour out ultraviolet radiation, illuminating the gas clouds around them and causing them to flourish, to glow, like cosmic neon signs. nebulae that appear as faint, ghostly wisps in visible light would blaze with color and structure in the ultraviolet. The birth of stars happening right now in nebulae throughout our galaxy would be dramatically visible. But the ultraviolet sky also reveals something else. It shows us the most violent processes in the universe, the accretion disks around white dwarfs in binary systems, the hot surfaces of young stars, the shocked gas from supernova explosions expanding into interstellar space. The ultraviolet universe is a universe of extremes, of creation and destruction, of birth and death playing out on cosmic scales. Further still, we reach the X-ray sky. If you could see X-rays, you would see a universe of breathtaking violence. X-rays are produced in the most extreme environments in the cosmos, where matter is heated to millions or even billions of degrees. You would see the remnants of exploded stars, supernova remnants, expanding shells of superheated gas glowing fiercely in X-rays. You would see the coronae of stars, their outer atmospheres heated to millions of degrees by magnetic activity. You would see gas falling into black holes, spiraling inward at tremendous speeds, heating up through friction until it emits X-rays more powerful than the combined output of an entire galaxy. You would see clusters of galaxies, the largest gravitationally bound structures in the universe, filled with vast clouds of X-ray emitting gas at temperatures of tens of millions of degrees. The X-ray universe is a universe of superlatives, everything bigger, hotter, more energetic, more extreme than anything in the visible universe. And finally, at the extreme short wavelength end of the spectrum, we have gamma rays. These are the highest energy photons in the universe, produced by the most cataclysmic events imaginable. Gamma ray bursts, the most powerful explosions in the universe since the Big Bang, can outshine an entire galaxy for a few seconds, releasing more energy in those seconds than our sun will emit in its entire 10 billion year lifetime. Magnetars, neutron stars with magnetic fields a quadrillion times stronger than Earth's, occasionally undergo starquakes that release colossal bursts of gamma rays, and the annihilation of matter with antimatter produces gamma rays with a very specific energy signature, and this signature has been detected coming from the center of our galaxy, telling us that matter and antimatter are meeting and destroying each other right now in the chaotic environment around our galaxy's central black hole. The gamma ray sky is a sky of apocalyptic fury, a constant reminder that the universe is not a gentle place. So here is the profound realization. Space is dark only if you define dark as the absence of visible light. But visible light is just one tiny frequency band out of the vast electromagnetic spectrum. If you expand your definition to include all forms of light, all wavelengths of electromagnetic radiation, then space is not dark at all. Space is flooded with light. It is drenched in photons. It is awash in radiation from one end of the spectrum to the other. The cosmic microwave background alone fills every cubic centimeter of space with about 400 photons. 400 photons in every cubic centimeter, everywhere in the universe. That is not darkness. That is an ocean of light. We are swimming in it right now, but we are blind to it. The darkness we perceive is not a property of the universe. It is a property of us. It is a consequence of our biological limitations, of the narrow window through which our evolved eyes view the cosmos. The universe is singing a symphony of light, and we can hear only one note. This realization leads to a deeper question, one that should make any thoughtful person pause. If our eyes showed us only a tiny fraction of reality, what else might we be missing? What other aspects of the universe are invisible to us, not because they don't exist, but because we lack the senses to perceive them? This question will become very important later, when we discuss dark matter and dark energy. But for now, let us return to the story of light in the universe, because there is a particular light, the oldest light in existence, that has an extraordinary story to tell. The cosmic microwave background radiation is, without exaggeration, one of the most important discoveries in the history of science. It is also one of the most accidental. The story of its discovery is one of those wonderful episodes in the history of science where a profound truth reveals itself not through years of careful planning and deliberate experimentation, but through serendipity, through being in the right place at the right time, and crucially, being smart enough to recognize the significance of what you found. It was 1964, and two young radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Labs in Holmdel, New Jersey, using a large horn-shaped antenna originally built for satellite communication experiments. They had repurposed the antenna for radio astronomy and were trying to make precision measurements of radio emissions from the Milky Way. But they had a problem. No matter where they pointed the antenna, no matter what direction they looked, they detected a persistent low-level noise, a faint hiss of microwave radiation that they could not get rid of. They checked the antenna for defects. They tightened all the connections. They discovered that a pair of pigeons had been nesting inside the horn of the antenna and had coated its interior with what Penzias and Wilson delicately referred to in their notes as a white dielectric material, which is a scientific way of saying pigeon droppings. They removed the pigeons and carefully cleaned out all the droppings. The noise remained. They checked for interference from nearby cities, from military radar, from the antenna itself. Nothing worked. The noise was always there, always the same intensity, always the same in every direction. It was isotropic, meaning it was completely uniform across the entire sky. And it had a temperature of about 3.5 Kelvin, just a few degrees above absolute zero. Penzias and Wilson were frustrated and puzzled. They didn't know what they were detecting. But not far away at Princeton University, a group of physicists led by Robert Dick and Jim Peebles did know, or rather, they had predicted exactly this kind of radiation and were in the process of building their own antenna to search for it. Dick and Peebles had worked out that if the Big Bang theory was correct, the universe should be filled with a faint afterglow of microwave radiation, the remnant of the intensely hot plasma that filled the universe in its earliest moments. When the universe was very young, less than about 380,000 years old, it was so hot and dense that electrons and protons couldn't combine to form atoms. The universe was a seething plasma, a fog of charged particles that was opaque to light. Photons were constantly being emitted and absorbed, scattered in every direction. They couldn't travel more than a short distance before being scattered again. The universe was, in a sense, blindingly bright, but the brightness was trapped, unable to escape the plasma, unable to travel freely through space. But as the universe expanded, it cooled, and when the temperature dropped to about 3000 Kelvin, something magical happened. Electrons and protons could finally combine to form neutral hydrogen atoms. This event, known as recombination, occurred approximately 380,000 years after the Big Bang, and it changed everything. Neutral atoms are transparent to most wavelengths of light. Suddenly, the fog lifted. The photons that had been trapped, bouncing from particle to particle, were free. They could travel in straight lines through the newly transparent universe. This moment is called the surface of last scattering, and the photons released at that moment have been traveling through space ever since, for 13.8 billion years. They are still traveling through space right now. They are everywhere, filling every cubic centimeter of the universe, a relic of the moment when the cosmos first became transparent. But they are no longer the brilliant orange glow they were when they were released. The expansion of the universe has stretched their wavelengths by a factor of about 1100, shifting them from visible light deep into the microwave part of the spectrum. Their temperature has dropped from 3000 Kelvin to just 2.725 Kelvin. They are now the cosmic microwave background, a cold, faint whisper of the universe's fiery birth. When Penzias and Wilson heard about the Princeton group's prediction through a mutual contact, they realized what they had found. The persistent noise in their antenna was not a flaw, not pigeon droppings, not interference. It was the echo of the Big Bang itself. They had accidentally detected the oldest light in the universe, light that had been traveling for nearly 14 billion years, light that carried within it the secrets of the universe's origin and structure. For this discovery, Penzias and Wilson were awarded the Nobel Prize in Physics in 1978. It remains one of the most important scientific discoveries ever made. But the CMB is not just a historical curiosity. It is an extraordinarily rich source of information about the universe. Over the decades since its discovery, it has been measured with increasing precision by a series of space missions, from COBE in 1989 to MAP in 2001 to Planck in 2009. Each mission revealed the CMB in greater detail, and each time the results were stunning. The CMB is astonishingly uniform. Its temperature is the same in every direction to a precision of 1 part in 100,000. This tells us that the early universe was incredibly smooth and homogeneous, that matter and energy were distributed almost perfectly evenly in the first moments after the Big Bang. But it is the tiny variations, those 1 part in 100,000 fluctuations, that are truly remarkable. These fluctuations correspond to slightly denser and slightly less dense regions in the early universe. The slightly denser regions had slightly stronger gravitational fields, which pulled in more matter over time, growing denser and denser until eventually they collapsed to form galaxies, stars, and planets. The slightly less dense regions became the voids, the great empty spaces between the filaments of the cosmic web. Every structure in the universe, from the largest galaxy clusters to the smallest planets to you and me, traces its ancestry back to these tiny quantum fluctuations, frozen into the CMB like a cosmic fingerprint. The CMB has also given us the most precise measurements of the fundamental properties of the universe. From the pattern of fluctuations in the CMB, cosmologists have determined that the universe is approximately 13.797 billion years old, with an uncertainty of about 20 million years, a precision of better than 0.2%. They have determined that the universe is spatially flat, meaning that the geometry of space on the largest scales follows the rules of ordinary Euclidean geometry, the geometry you learned in school. They have determined the composition of the universe, about 5% ordinary matter, the stuff that makes up stars, planets, and people, about 27% dark matter, a mysterious substance that we can detect only through its gravitational effects, and about 68% dark energy, an even more mysterious force that is causing the expansion of the universe to accelerate. All of this from a faint microwave hiss that was initially mistaken for pigeon droppings. Now I want to connect this back to our central theme, the darkness of space. Before the CMB was released, before recombination, the universe was not dark. It was the opposite of dark. It was a blazing, opaque fog of plasma glowing at thousands of degrees. Every direction was bright. There was no dark sky, no dark space, no concept of darkness at all. The universe was a furnace of light. Darkness came later. Darkness was a consequence of the universe cooling, of atoms forming, of space becoming transparent. The darkness of space is not primordial. It is not original. It is a relatively recent development in the history of the cosmos. The universe went from light to dark, from opaque brightness to transparent darkness. And as we will see later, the story doesn't end there. The universe is on a trajectory toward an even deeper, more permanent, more absolute darkness than anything we see today. But I'm getting ahead of myself. Let me ask you a question. If you could somehow go back in time to just before recombination, to the universe at an age of say 300,000 years, what would you experience? You would not be floating in dark, empty space with distant galaxies scattered around you. There were no galaxies yet, no stars, no planets. You would be engulfed in a hot, glowing plasma. In every direction, all you would see is a brilliant orange-white glow, like being inside the photosphere of a star. You could not see more than a few meters in any direction because the plasma was opaque. Light was being scattered constantly, absorbed and re-emitted, bouncing in every direction. There was no concept of distance, no horizon, no night, no day. Just light, everywhere, in every direction, at every moment. And then, over a period of several thousand years as the temperature dropped, the glow would gradually shift from white to orange to red, and then it would begin to fade, becoming dimmer and dimmer as the universe expanded and the plasma cooled. Atoms would form, the fog would lift, and suddenly, you could see. For the first time in the history of the universe, photons could travel in straight lines. You could see into the distance. But there would be nothing to see. No stars had formed yet. No galaxies existed. Just vast, expanding clouds of neutral hydrogen and helium gas, cooling and darkening. The glow of the CMB, now released and fading, would shift from a dim red through infrared and into invisibility. And you would be left in darkness. Not the comfortable darkness of a room with the lights off. A darkness more complete than anything on Earth. No stars, no galaxies, no light sources of any kind. Just cold, expanding gas in an ever-growing void of space. This period is known as the Cosmic Dark Ages, and it lasted for roughly 200 million years, from recombination at about 380,000 years after the Big Bang until the formation of the first stars. It was, quite literally, the darkest period in the history of the universe. Can you imagine that? 200 million years of absolute darkness. No light anywhere in the entire universe except the fading, cooling, invisible afterglow of the Big Bang. If the universe were a day, the Cosmic Dark Ages would be a long, silent night between the dying glow of the Big Bang and the first glimmer of starlight. And during those dark ages, something extraordinary was happening, silently, invisibly, in the darkness. Gravity was at work. The tiny density fluctuations left over from the Big Bang, those 1 part in 100,000 variations in the CMB, were acting as seeds. Regions that were slightly denser than average had slightly stronger gravitational fields. They pulled in gas from their surroundings, becoming denser still. This process of gravitational collapse, operating in silence and darkness over hundreds of millions of years, gradually built up the first concentrations of matter dense enough to ignite nuclear fusion. And then, somewhere in the universe, for the first time, a star was born. The first stars were nothing like our Sun. They were monsters, with no heavy elements to help the gas cool and fragment. The first collapsing gas clouds produced enormous stars, hundreds of times more massive than the Sun, maybe even 1,000 times more massive. These population 3 stars, as they are called, because they were the first generation of stars and astronomers count backward, were incredibly hot, incredibly luminous, and incredibly short-lived. They burned through their nuclear fuel in just a few million years, compared to the 10 billion year lifetime of a star like our Sun. But during their brief lives, they poured out torrents of ultraviolet radiation that began to ionize the surrounding neutral hydrogen gas, clearing bubbles of transparent, ionized gas around them. As more and more first-generation stars formed throughout the universe, these bubbles grew and merged, gradually reionizing the entire universe in a process called the Epoch of Reionization. The Cosmic Dark Ages were ending. The lights were coming on. This is one of the most dramatic transitions in the history of the universe, and it is also one of the least well understood. We can see the CMB from before the Dark Ages, and we can see galaxies from after the Dark Ages, but the Dark Ages themselves and the very beginning of the Epoch of Reionization remain largely hidden from us. They are one of the last great frontiers in observational cosmology. The James Webb Space Telescope, launched in December 2021, is designed in part to peer into this era, to detect the light from the very first galaxies that formed at the end of the Dark Ages. And GUST has already delivered stunning results, finding galaxies that formed astonishingly early. Just a few hundred million years after the Big Bang, galaxies that are brighter and more massive than our theoretical models predicted. These discoveries are challenging our understanding of how quickly the first structures in the universe could form, and how quickly the Dark Ages could end. The darkness is reluctantly giving up its secrets, but there is still so much we don't know. And this brings me to a point that I find deeply profound. The universe's story, in terms of light and darkness, follows a dramatic arc. It begins with the blinding, opaque brightness of the hot Big Bang. Then comes the cooling, the formation of atoms, and the transition to transparent darkness, the cosmic dark ages. Then the first stars ignite, and for the first time, localized sources of light appear in the darkness, islands of nuclear fire in an ocean of void. Over billions of years, galaxies form, grow, merge, and evolve, filling the universe with the light of hundreds of billions of stars in each of hundreds of billions of galaxies. This is where we are now, in the bright era of the universe, the age of starlight. But as we will discuss soon, this bright era is temporary. The fuel that powers the stars is finite. The expansion of the universe will eventually push most galaxies beyond our observable horizon. The stars will burn out, one by one, and a new darkness will descend. A final darkness, deeper and more permanent than the cosmic dark ages. The universe's story is a story of darkness, punctuated by a relatively brief episode of light. And we exist in that episode. We are the children of the light, the products of that brief, precious window of cosmic time when stars shine and complexity is possible. The darkness before us was empty. The darkness after us will be empty. We are the universe's fleeting attempt at light, at structure, at consciousness. That thought should fill you with a sense of urgency and wonder that is difficult to put into words. But before we look at the future, let me show you the darkest places in the universe as it exists right now. Because even in our current era of starlight and galaxies, there are places so dark, so empty, so devoid of light and matter, that they seem to defy the very concept of a universe filled with stuff. I want to take you on a tour of the cosmic voids, and I want you to feel, really feel, how empty and dark they are. I already mentioned the Boots Void, that spherical region about 330 million light-years across containing only about 60 galaxies where there should be thousands. Let me paint a more vivid picture of what it would be like to exist inside it. Our own Milky Way galaxy is part of a structure called the Local Group, a collection of about 80 galaxies, including the large Andromeda Galaxy and dozens of smaller dwarf galaxies, all gravitationally bound to each other within a region about 10 million light-years across. The Local Group is, in turn, part of a larger structure called the Virgo supercluster, which contains about 100 galaxy groups and clusters spread across a region about 110 million light-years in diameter. And the Virgo supercluster is part of an even larger structure called Laniakea, a supercluster of superclusters spanning about 500 million light-years. Our cosmic neighborhood is rich, dense, full of galaxies and galaxy clusters, connected by filaments of dark matter and gas. If you stand on Earth and look up at the night sky, you are seeing the light of stars in our own galaxy. But with a telescope, you can see thousands of other galaxies in every direction. The universe around us feels populated, alive. Now imagine being transplanted to the center of the Boots Void. Everything changes. The nearest galaxies are over 100 million light-years away. With the naked eye, you would see nothing but the stars of your own galaxy, assuming you had a galaxy, which is not guaranteed in the heart of the void. If you were on a solitary planet orbiting a solitary star in the deepest part of the Boots Void, you would look up at the night sky and see almost nothing. Your own star's planets, sure. Maybe a few nearby stars if you were part of one of those 60 lonely galaxies. But beyond that, blackness. No Milky Way stretching across the sky. No Andromeda Galaxy visible as a smudge. No nearby galaxy clusters forming patterns of light. Just an infinite seeming abyss of darkness in every direction. Your astronomers, if your civilization developed them, would have a much harder time discovering the true nature of the universe. They would have fewer nearby galaxies to study, fewer gravitational lenses to exploit, fewer data points for measuring cosmic expansion. The darkness around them would be not just a visual phenomenon, but an intellectual barrier, a limit on what they could learn about the cosmos. But the Boots Void is not even the most extreme example. There are larger voids. The The KBC void, named after Keenan, Barger and Cowie who identified it, may be up to 2 billion light-years in diameter, and some evidence suggests that our own local group might be located inside it, or at least near its edge. If this is true, then we ourselves are living in a region of the universe that is less dense than average. The galaxies we see around us, the rich cosmic landscape we use to study the universe, is actually an underdense region. A civilization living in a truly average density region of the universe would see more galaxies in every direction than we do. This is a humbling thought. Even our cosmic neighborhood, which seems so full of stuff, is relatively empty compared to the densest parts of the cosmic web. And the densest parts of the cosmic web, the galaxy clusters at the intersections of the filaments, are themselves mostly empty space. The voids are the norm, the galaxies are the exception. Darkness is the default state of the universe, and light is the anomaly. Then there is the CMB cold spot, one of the most puzzling features in the entire sky. It is an anomalously cold region in the cosmic microwave background, located in the southern sky in the direction of the constellation Eridanus. The temperature difference is small, on the order of 70 millionths of a Kelvin colder than average, but in the exquisitely uniform CMB, this is a significant deviation. One proposed explanation is that the cold spot is caused by a vast supervoid in the cosmic web, a region of space up to 1.8 billion light-years across that is even emptier than the Bootes void. When CMB photons pass through this supervoid, they lose a tiny amount of energy due to an effect related to the accelerating expansion of the universe, and this makes the CMB slightly cooler in that direction. But here is what makes the cold spot truly fascinating. Some physicists have proposed an even more exotic explanation. They suggest that the cold spot might not be a supervoid at all. It might be the imprint of another universe. According to certain models of eternal inflation, our universe is just one bubble in an infinite sea of universes, a multiverse. If our bubble universe collided with or came into contact with another bubble universe at some point in its early history, the collision could leave a mark on the CMB, a cold or hot spot that would look exactly like an anomalous temperature fluctuation. If the cold spot is evidence of such a collision, it would be the first observational evidence for the existence of other universes, a discovery that would rank among the most important in the history of human knowledge. We don't know if this explanation is correct. It is speculative, and there are more conventional explanations for the cold spot. But the mere possibility is intoxicating. That a dark, cold patch in the microwave sky could be a window into the multiverse, a point of contact between our reality and another, is the kind of idea that makes cosmology feel more like science fiction than science. Let me show you another kind of darkness, a more intimate kind. Within our own galaxy, there are regions of darkness so profound that early astronomers thought they were looking at actual holes in the sky, gaps in the fabric of the stars, through which the darkness of empty space beyond could be seen. They called them dark nebulae, and the most famous examples include the Coalsack Nebula in the southern sky, the Horsehead Nebula in Orion, and the wonderfully named Barnard 68, a dense molecular cloud about 500 light-years away that appears in photographs as a perfectly opaque black blob against a rich background of stars. Not a single star is visible through Barnard 68 in visible light. It looks as if someone took a hole punch to the sky. But Barnard 68 is not a hole. It is not empty. It is not a window into a deeper darkness. It is in fact the opposite of empty. It is one of the densest regions of gas and dust in our galaxy, a molecular cloud with a mass of about 2 solar masses compressed into a sphere just half a light-year across. The cloud is so dense with dust particles that it absorbs virtually all the visible light from the stars behind it. No photon of visible light can make it through. In visible light, it is as dark as anything in the universe. But remember what we said about the electromagnetic spectrum. If you look at Barnard 68 in infrared light, the opacity fades. Infrared photons, with their longer wavelengths, can weave their way between the dust grains. Stars that are completely invisible in visible light pop into view in the infrared, shining through the cloud as if the darkness were merely a thin veil. The cloud itself glows faintly in the far infrared, its dust grains warmed to a few degrees above absolute zero by the diffuse starlight of the galaxy. And within the cloud, something extraordinary is happening. The gas is slowly contracting, pulled inward by its own gravity. Over the next 100,000 years or so, the core of Barnard 68 will become dense enough and hot enough to ignite nuclear fusion, and a new star will be born. The darkness of the cloud is not permanent, it is temporary. It is the darkness of a cocoon, a darkness that precedes birth. Right now, at this moment, in the darkest, most opaque region of this molecular cloud, the raw material of a future solar system is assembling itself. Future planets may form, life might eventually emerge. And it is all happening in darkness, in silence, in a black blob that looks like nothing at all. There is something profoundly poetic about that. The darkest places in the galaxy are not dead ends, they are beginnings. Darkness in this context is not the absence of something, it is the presence of potential, the calm before the ignition, the inhale before the first breath. This brings me to a topic that I find endlessly fascinating and deeply unsettling in equal measure. What happens to the human mind in true darkness? We have been talking about the physical darkness of space, the absence of photons, the empty voids between galaxies, the opaque clouds of interstellar dust. But darkness has a psychological dimension too, and it is just as profound and just as terrifying as the physical one. Humans are, fundamentally, creatures of light. Our most dominant sense is vision. We process more of our sensory information through our eyes than through all our other senses combined. Our brains devote an enormous fraction of their processing power to visual information, interpreting patterns, recognizing faces, judging distances, detecting motion. When you remove visual input, when you place a human being in true darkness, something very strange begins to happen to the brain. In the 1950s and 60s, researchers at McGill University in Montreal conducted a series of now famous experiments in sensory deprivation. Volunteers were placed in small, isolated rooms with no light, no sound, and minimal tactile stimulation. They wore padded gloves to reduce touch sensation, translucent goggles to eliminate patterned vision, and ear covers that reduced auditory input to a constant low hum. The researchers expected the volunteers to simply find the experience boring. What actually happened was far more dramatic. Within hours, many subjects began to experience vivid hallucinations. Not vague, dreamlike impressions, but full-blown, detailed, three-dimensional hallucinations of objects, people, landscapes, and geometric patterns. Some subjects saw processions of squirrels marching across their visual field, carrying tiny sacks. Others saw complex architectural structures, heard voices speaking clearly, or felt the presence of other people in the room with them. As the hours wore on, many subjects became increasingly anxious, disoriented, and paranoid. Their ability to think clearly and logically deteriorated. Some experienced intense emotional swings, alternating between euphoria and terror. Several subjects became so distressed that they demanded to be released from the experiment within 24 hours. A few lasted longer, but the psychological effects only intensified with time. After several days, some subjects exhibited signs of psychosis, unable to distinguish their hallucinations from reality, losing their sense of identity and their grip on the flow of time. What was happening? The answer lies in the way our brains process sensory information. Your brain is not a passive receiver of data. It is an active generator of reality. At every moment, your brain is constructing a model of the world around you based on sensory input. When the input is rich and consistent, the model is stable and accurate. You see the room around you, hear the sounds, feel the surfaces, and your brain's model matches the external world. But when sensory input is removed, your brain doesn't stop generating the model. It can't. The neural circuits that construct your perceptual reality are always active, always running. Without external data to constrain them, they begin to generate their own content, drawing on memories, expectations, fears, and random neural noise to create a hallucinatory reality. Your brain is so desperate for input that it invents its own. The hallucinations of sensory deprivation are not a malfunction. They are your brain doing exactly what it always does, constructing reality, but without the raw materials of sensory data to keep the construction anchored to the external world. Now think about what this means for a human being in deep space. An astronaut on a long-duration mission between stars, if such a mission were ever attempted with current or near-future technology, would spend years in an environment where the visual landscape outside the spacecraft is essentially unchanged. The same stars in the same positions day after day, month after month, year after year. Stars don't visibly move on human timescales. The view out the window is a frozen tableau of tiny bright points on absolute blackness. There is no weather, no sunrise, no sunset, no change of seasons, no cloud formations, no horizon, no landscape, no visual complexity of any kind. Just the static, unchanging void. The psychological effects of this environment over extended periods are largely unknown, because no human has ever experienced it. But based on what we know from sensory deprivation research, from accounts of polar explorers enduring months of perpetual darkness, from studies of submarine crews on extended underwater deployments, the outlook is concerning. Prolonged exposure to an unchanging, visually impoverished environment can lead to depression, cognitive decline, hallucinations, interpersonal conflict, and a gradual erosion of the sense of meaning and purpose that keeps the human mind functioning. The darkness of deep space is not just a physical phenomenon, it is a psychological weapon, and any future civilization that attempts interstellar travel will have to reckon with its effects on the human mind. There is one more aspect of the space darkness experience that I want to mention, because it is genuinely strange. Astronauts, beginning with the Apollo missions, have reported seeing flashes of light when they close their eyes in the darkness of space. These are not hallucinations, they are real, and they have a physical cause. High-energy cosmic rays, subatomic particles traveling through space at nearly the speed of light, sometimes pass through the spacecraft and through the astronaut's body, including their eyes. When a cosmic ray particle passes through the vitreous humor of the eye or interacts with the retinal cells, it can produce a flash of visible light, either through Cherenkov radiation, which is the optical equivalent of a sonic boom, or by directly stimulating the retinal cells. Astronauts describe these flashes as streaks, dots, or brief starbursts that appear even when their eyes are closed, even in total darkness. It is a reminder that even in the darkest environment accessible to humans, the void of near-Earth space, you are being constantly bombarded by particles from the most violent events in the universe, supernova explosions, black hole jets, and the remnants of the Big Bang itself. The darkness is not as empty as it seems. It is alive with invisible energy, and your body can detect it, if only as brief, ghostly flashes behind your closed eyelids. This brings me to a philosophical dimension of cosmic darkness that I think is worth dwelling on, because it touches something deep in the human psyche. Blaise Pascal, the 17th century French mathematician and philosopher, wrote one of the most famous lines in all of Western thought. The eternal silence of these infinite spaces frightens me. Pascal was writing in an era when the true scale of the universe was just beginning to be appreciated. When the comfortable medieval cosmos of crystalline spheres and divine order was giving way to the terrifying vista of infinite empty space that the new astronomy revealed. And Pascal's fear was not irrational. It was, in many ways, the only rational response to the realization that the universe is vast beyond comprehension, empty beyond imagination, and utterly indifferent to human existence. Modern cosmology has only intensified Pascal's terror. The universe is not just big. It is big in a way that defies every attempt at comprehension. The observable universe is 93 billion light-years in diameter, and it may be infinitely larger beyond the horizon we can see. It contains on the order of 2 trillion galaxies, each containing hundreds of billions of stars, spread across a volume of space so vast that the numbers become meaningless. and most of that volume is empty, dark, void. The galaxies are like a few grains of sand scattered across a beach the size of a continent. The stars within those galaxies are like atoms within those grains of sand, and the space between is nothing. Darkness, silence, an absence so complete that the human mind recoils from it. Our brains evolved on the African savanna, under skies that seemed intimate and close, in a world where the farthest visible object was a mountain on the horizon. We are not equipped, neurologically or psychologically, to confront the true scale of cosmic emptiness. When we try, something in us flinches. We feel a vertigo, a nausea of the mind, a sense of falling that is not physical but existential. This feeling has a name. Some call it cosmic horror. Some call it the sublime. Some call it the overview effect's dark counterpart. Whatever you call it, it is a consequence of a finite mind confronting an infinite darkness, and it is, I think, one of the most profound experiences available to a conscious being. But I don't want to leave you in that dark place, metaphorically speaking. Because there is another way to look at it, a way that I find far more compelling and far more beautiful. Yes, the universe is vast and dark and mostly empty. Yes, we are tiny and temporary, and seemingly insignificant. But consider this. We are the only things in the known universe that can look at the darkness and wonder about it. As far as we know, in the entire observable universe, only here, on this small rocky planet orbiting an average star in an average galaxy, has the universe produced beings who can contemplate their own existence, ask why the sky is dark, and figure out the answer. We are, as the astronomer Carl Sagan said, a way for the cosmos to know itself. The darkness out there is vast and empty and silent, but in here, inside our minds, inside the 3 pounds of neural tissue inside our skulls, there is light. The light of understanding. The light of curiosity. The light of consciousness. And that light, however small it may be in the grand scheme of things, is the only light of its kind that we know of in the entire universe. That makes it precious beyond measure. It makes us precious beyond measure. Not despite the darkness, but because of it. The darkness gives the light its meaning. Now let us talk about something that will take the concept of cosmic darkness to an entirely new level. Let us talk about the future. Because if you think the darkness of space is unsettling now, wait until you hear what's coming. The universe is not just dark, it is getting darker. And it will continue to get darker, relentlessly, inexorably, until a darkness so complete and so permanent descends that it will make the current state of the cosmos look like a blazing fireworks display. This is not speculation. This is not science fiction. This is the straightforward, mathematically inevitable consequence of the physical laws that govern our universe. And it is, depending on your temperament, either the most depressing or the most profound thing you will ever learn. The story begins with a discovery that was made in 1998. A discovery so unexpected and so disturbing that the scientists who made it initially didn't believe their own results. 2 independent teams of astronomers, the Supernova Cosmology Project led by Saul Perlmutter and the High Z Supernova Search Team led by Brian Schmidt and Adam Rees, were studying distant Type 1a supernovae. Type 1a supernovae are a particular type of stellar explosion that occurs when a white dwarf star in a binary system accumulates enough matter from its companion star to push it over the Chandrasekhar limit of about 1.4 solar masses. The resulting thermonuclear explosion is incredibly bright and, crucially, has a very consistent peak luminosity. Because they all explode with roughly the same brightness, Type 1 supernovae can be used as standard candles. By comparing their apparent brightness, how bright they look from Earth, with their known intrinsic brightness, astronomers can calculate their distance. And by measuring the redshift of the galaxies they occurred in, astronomers can determine how fast those galaxies are receding from us. Plot distance against recession speed, and you get the expansion history of the universe. Both teams expected to find that the expansion of the universe was decelerating, slowing down over time. This was the natural expectation. The universe is full of matter, and matter has gravity, and gravity pulls things together. The gravitational attraction of all the matter in the universe should be acting as a brake on the expansion, gradually slowing it down since the Big Bang. The only question was how quickly the expansion was decelerating. Was it decelerating fast enough that the universe would eventually stop expanding and collapse back on itself in a big crunch? Or was it decelerating slowly enough that the expansion would continue forever, gradually slowing but never quite stopping? What both teams found, to their shock and disbelief, was neither of these options. The expansion of the universe was not decelerating at all. It was accelerating. The expansion was speeding up. Distant supernovae were farther away than they should have been if the expansion was slowing down. Something was pushing the universe apart, overcoming the gravitational attraction of all the matter in the cosmos, and the expansion was getting faster over time. This was, by any measure, one of the most surprising discoveries in the history of physics. Perlmutter, Schmidt, and Rius were awarded the Nobel Prize in Physics in 2011. And the name given to the mysterious force driving the acceleration was dark energy. We still don't know what dark energy is. Let me be clear about that. Despite more than 2 decades of intense theoretical and observational work, dark energy remains one of the deepest mysteries in all of science. We know what it does. It causes the expansion of the universe to accelerate. We know how much of it there is. It makes up about 68% of the total energy content of the universe, making it the dominant component by far. We know its approximate equation of state, the relationship between its pressure and its energy density. But we don't know what it is. We don't know why it exists. We don't know if it has always been the same strength or if it changes over time. We don't even know if it is a property of space itself, as Einstein's cosmological constant suggests, or if it is a new kind of energy field, what some physicists call quintessence, or if it is a sign that our theory of gravity, general relativity, needs to be modified on cosmological scales. Dark energy is not just a gap in our knowledge, it is a chasm. The dominant component of the universe, the force that will determine its ultimate fate, and we have almost no understanding of what it actually is. Recent results from the Dark Energy Spectroscopic Instrument, DESI, which has been mapping the 3-dimensional positions of tens of millions of galaxies to study the expansion history of the universe in unprecedented detail, have added a new twist to the story. Some early DESI results have hinted that dark energy may not be constant over time. Its strength may be changing, evolving, as the universe ages. If this is true, it could fundamentally alter our predictions for the future of the cosmos. A changing dark energy could lead to a future very different from the standard prediction of eternal accelerating expansion. It could potentially lead to a future where the expansion reverses, or where dark energy grows stronger without limit, eventually tearing apart galaxies, stars, planets, and even atoms in a cataclysmic Big Rip. But these results are still preliminary, still uncertain, still being analysed and debated. For now, the standard model of cosmology assumes that dark energy is constant, that it has always been the same strength and always will be. And if that is the case, the future of the universe is one of ever-increasing darkness. Here is the timeline, and I want you to follow it carefully, because each step is more haunting than the last. Right now, the universe is about 13.8 billion years old, and we live in what cosmologists call the stelliferous era, the era of stars. This is the era in which nuclear fusion lights up galaxies across the observable universe, in which heavy elements are forged in stellar interiors and supernova explosions, in which planets form and life arises and consciousness emerges. It is a good time to be alive. But the stelliferous era is not permanent. It is a phase, a chapter in the universe's story, and it has a beginning and an end. Let us start with what is happening right now, at this moment, as you listen to this. The expansion of the universe is carrying distant galaxies away from us. The farther away a galaxy is, the the faster it recedes. And because the expansion is accelerating due to dark energy, galaxies that are currently near the edge of the observable universe are receding from us at speeds greater than the speed of light. This sounds like it should be impossible, since nothing can travel through space faster than light. But this is not traveling through space. This is space itself expanding, carrying the galaxies along with it. There is no speed limit on the expansion of space, and because these galaxies are receding faster than light, any new light they emit right now will never reach us. They are beyond our cosmic event horizon, our causal horizon, the boundary beyond which events can never have any effect on us, no matter how long we wait. And here is the chilling part, that boundary is getting closer. As the expansion accelerates, more and more galaxies are being pushed beyond the event horizon. One by one, galaxies that we can currently see are crossing the threshold and becoming permanently unreachable, permanently invisible. Their light is being stretched to longer and longer wavelengths by the expansion of space, redshifted toward infinity, fading, dimming, and eventually vanishing entirely. We are, right now, at this moment, watching the universe disappear. Fast forward. In about 100 billion years, roughly 7 times the current age of the universe, every galaxy beyond our local group will have receded past the cosmic event horizon. The local group, the collection of galaxies gravitationally bound together with our Milky Way, including Andromeda and a few dozen smaller galaxies, will have merged into a single large elliptical galaxy, sometimes called Milkdromeda. And that will be it. That will be the entire visible universe. One galaxy, surrounded by a vast empty darkness stretching to infinity in every direction. The CMB will have been redshifted to wavelengths so long that it will be undetectable. There will be no evidence, none whatsoever, that other galaxies ever existed. No evidence that the universe is expanding, no evidence for the Big Bang. A civilization born in that era, living in the merged Milkdromeda galaxy, looking out at the sky, would see their galaxy and nothing else. They would conclude that the universe consists of one galaxy surrounded by infinite, static, empty, dark space. And they would be wrong, but they would have no way to know they were wrong. All the evidence of the true nature of the universe, the expansion, the other galaxies, the CMB, the Big Bang, would have been erased by the expansion itself. The darkness would not just be physical. It would be an informational darkness, a darkness of lost knowledge, a cosmic censorship that hides the truth from any civilization unfortunate enough to arise too late. I find this thought deeply disturbing. The idea that the universe is actively erasing evidence of its own history, that the physical laws governing the cosmos will eventually make it impossible to determine the truth about the cosmos, strikes at something fundamental in the scientific worldview. Science is built on the assumption that the universe is comprehensible, that evidence exists to be found, that truth is accessible through observation and reason. But in the far future, the truth will be inaccessible. The evidence will be gone. The darkness will be complete, not just physically, but epistemologically. But we are not done. The story gets even darker. Fast forward further to about 100 trillion years from now, roughly 10,000 times the current age of the universe. By this time, the last stars have burned out. The stelliferous era is over. Star formation has ceased because the raw materials, the gas and dust from which new stars form, have been used up or dispersed beyond recovery. The last red dwarfs, the smallest, faintest, longest-lived stars in the universe. Stars that burn their hydrogen fuel so slowly that they can shine for trillions of years, have finally exhausted their fuel and cooled to invisibility. What remains are the stellar corpses, white dwarfs, the dense remnants of sun-like stars, slowly cooling and darkening over billions of years. Neutron stars, the ultra-dense remnants of more massive stars, also slowly cooling. Black holes, the gravitational tombstones of the most massive stars, silently lurking in the darkness. and a vast quantity of substellar objects, brown dwarfs, rogue planets, asteroids and debris, too small to ever have ignited nuclear fusion, drifting endlessly through the void. This is the degenerate era, an era of darkness and decay, an era in which the universe is populated by the slowly cooling remnants of a once brilliant civilization of stars. During the degenerate era, the universe is dark, but it is not quite completely dark. White dwarfs still emit a feeble glow as they cool, fading from white to yellow to orange to red to deep infrared over trillions of years. Occasionally, a close encounter between two stellar remnants might produce a brief flare of energy, a collision or a tidal disruption. Brown dwarfs in binary systems might occasionally merge to form a new hydrogen-burning star, a brief lonely flicker of light in an otherwise dark universe, a candle lit for a few billion years before the darkness closes in again. These events would be extraordinarily rare, separated by vast stretches of time and space, but they would happen. The degenerate era is not dead, it is dying. Slowly, quietly, one last gasp at a time. Eventually, even these faint glimmers will cease. The white dwarfs will cool to black dwarfs, objects at the same temperature as the cosmic background, invisible, undetectable, dead. This cooling process takes an incomprehensibly long time. Estimates suggest that the first black dwarfs won't form for about 10 to the 15th power years, a quadrillion years, roughly 100,000 times the current age of the universe. When they do, they will be among the darkest objects in the cosmos. Cold, dark, inert spheres of crystallized carbon and oxygen, the final form of what were once brilliant, life-giving stars. But the story is not over even then, because the black holes remain, and the black hole era is coming. In the far, far future, long after the last white dwarfs have cooled to black dwarfs, the only significant objects left in the universe will be black holes. Stellar mass black holes, formed from the collapse of massive stars, with masses of a few to a few dozen solar masses. Intermediate mass black holes, with masses of hundreds to thousands of solar masses. And supermassive black holes, the behemoths at the centers of galaxies, with masses of millions to billions of solar masses, over inconceivably long timescales. Gravitational interactions between the remnants of the galaxy will gradually feed matter into the central supermassive black hole. Stars, black dwarfs, neutron stars, and other objects will slowly spiral inward over trillions of years, eventually crossing the event horizon and adding to the black hole's mass. Others will be gravitationally ejected from the galaxy entirely, flung into intergalactic space to drift alone forever. Eventually, the galaxy will have evaporated, its matter either consumed by the central black hole or dispersed into the void. What remains is a collection of black holes of various sizes, scattered through a universe that is otherwise empty. And here is where we encounter the most extreme darkness the universe has to offer. A black hole is, by definition, a region of space-time from which nothing can escape, not even light. The event horizon is the ultimate boundary, the ultimate darkness. No photon that crosses the event horizon will ever be seen again by the outside universe. Inside the event horizon, all paths through space-time lead inward, toward the singularity. There is no going back, no escape, no signal, no light. It is the darkest darkness possible within the laws of physics, a darkness that is not merely the absence of light, but the active gravitational imprisonment of light. If you were to fall into a supermassive black hole, your experience would depend on the size of the black hole. For a stellar mass black hole, the tidal forces near the event horizon would be enormous, stretching you from head to toe and compressing you from side to side in a process known as spaghettification. You would be killed long before you reached the event horizon. But for a sufficiently large supermassive black hole, the event horizon is so far from the singularity that the tidal forces there are gentle. You could cross the event horizon without even noticing. One moment you are outside, the next you are inside, and from your perspective, nothing special happened. No wall, no barrier, no flash of light or darkness, just a point in space that you crossed, after which your fate is sealed. Looking outward, back toward the universe you left behind, you would see the light from the outside universe increasingly blue-shifted and concentrated into a shrinking circle above you as you fell inward. The rest of the sky in every other direction would be absolute blackness, and as you fell deeper, the circle would shrink and brighten, compressing the entire history of the outside universe into an ever narrower beam until, at the singularity, or at whatever quantum gravitational structure replaces the singularity in a more complete theory, your journey would end. What happens at the singularity is unknown. Our physics breaks down. General relativity predicts infinite density, infinite curvature, the end of space and time. But we know that this prediction cannot be the full truth, because quantum mechanics must play a role at such extreme conditions, and we do not yet have a theory of quantum gravity to tell us what really happens. The center of a black hole is not just a region of darkness. It is a region of ignorance, a place where our understanding of the universe fails. But even black holes are not eternal. In 1974, the British physicist Stephen Hawking made one of the most extraordinary theoretical discoveries in the history of physics. Using a combination of general relativity and quantum field theory, Hawking showed that black holes are not perfectly black. They emit radiation. This Hawking radiation, as it came to be known, arises from quantum effects near the event horizon. In the vacuum of space, quantum mechanics dictates that particle-antiparticle pairs are constantly being created and annihilated, popping into existence and immediately recombining in a ceaseless quantum fizz. Normally, these virtual particles have no observable effects, but near the event horizon of a black hole, something remarkable can happen. One particle of a pair can fall into the black hole, while the other escapes. The escaping particle carries away energy, and by conservation of energy, the black hole must lose an equivalent amount of mass. Over time, this process causes the black hole to slowly shrink, losing mass and energy in the form of Hawking radiation. The temperature of this radiation is inversely proportional to the mass of the black hole. For a stellar mass black hole, the temperature is about 60 billionths of a Kelvin, far colder than the current CMB and utterly undetectable. For a supermassive black hole, it is even colder. But the temperature increases as the black hole shrinks, and as the black hole gets smaller, it evaporates faster, because a smaller black hole has a higher temperature and therefore emits radiation more quickly. In its final moments, the black hole's temperature skyrockets, its emission rate increases exponentially, and it evaporates completely in a final burst of radiation. The event horizon shrinks to nothing and the singularity is exposed, or, more likely, resolves into whatever quantum gravitational structure lies at the heart of a black hole, releasing its remaining mass energy in a flash. How long does this process take? For a stellar mass black hole of about 10 solar masses, the evaporation time is approximately 10 to the 67th power years. That is a 1 followed by 67 zeros. For comparison, the current age of the universe is about 10 to the 10th power years. The evaporation time of a stellar mass black hole is a number so large that it defies comprehension. It is not just a long time. It is a long time in the way that the observable universe is not just a big place. The scale is simply beyond the capacity of the human mind to grasp. And for the supermassive black holes at the centers of galaxies, with masses of billions of solar masses, the evaporation time is even more absurd, approximately 10 to the 100th power years, a googol years. A 1 followed by 100 zeros, written out in full. That number has more digits than there are atoms in the observable universe, but eventually, even this unimaginable span of time passes. The last black hole in the universe emits its final photon of Hawking radiation and vanishes, and with it goes the last significant concentration of mass energy in the cosmos. What remains is the Dark Era, the final chapter in the universe's story, a chapter that, as far as we know, lasts forever. The Dark Era is the heat death of the universe. It is the state of maximum entropy, maximum disorder, the thermodynamic end state from which no further work can be extracted, no further complexity can arise. The universe in the Dark Era consists of a thin, uniform soup of photons, neutrinos, electrons, and positrons, all at the lowest possible energies, spread across a space so vast that the average distance between any two particles is astronomical. The temperature of the universe approaches, but never quite reaches, absolute zero. There are no stars, no planets, no black holes, no structures of any kind. There is no light, no heat, no chemistry, no physics of interest. Just particles and radiation, slowly cooling, slowly diluting, slowly spreading apart as space continues to expand. Forever, this is the ultimate darkness. Not the darkness between stars, which is merely the darkness of distance. Not the darkness of a cosmic void, which is merely the darkness of underdensity. Not the darkness inside a black hole, which is the darkness of gravitational imprisonment. This is the darkness of thermodynamic death, the darkness that comes when the universe has exhausted all its potential for change, all its capacity for generating structure, all its ability to sustain anything remotely resembling interest or complexity or life. This is darkness as a permanent, irreversible state. The final darkness, the darkness that endures. I know this is heavy, I know it is bleak, but I want you to hold on to this for a moment, because there is a perspective shift coming that I think transforms this from a source of despair into a source of profound appreciation. And it is this: we are here, right now, in this moment, in the only era of cosmic history when any of this, any of the beauty, the complexity, the wonder of the universe is possible. The stelliferous era, the era of stars, represents a vanishingly small fraction of the total history of the universe. If you drew the timeline of the universe on a piece of paper, with the Big Bang on the left and the evaporation of the last black hole on the right, the entire stelliferous era, the entire period when stars shine and life is possible, would be so compressed to the left side of the diagram that it would be invisible. A sliver so thin that no pencil could draw it, no microscope could resolve it. We are living in the opening moments of the universe's story, and those opening moments are the only ones lit by starlight. Everything after is darkness. We are the fireworks at the beginning of an eternal night. Does that make you feel small? Maybe. But it also makes you feel incredibly, impossibly, absurdly lucky. Out of all the potential moments in the history of the cosmos, out of all the Googles of years of dark, cold, empty nothingness that stretch into the future, we exist here, now, in the brief flash of light. We are made of star stuff, as Sagan said, and we exist in the age of stars. That is not something to mourn. That is something to celebrate. If you are feeling the weight of that, if this perspective is hitting you somewhere deep, I want you to take a moment and drop a comment below. Tell me, does knowing the ultimate fate of the universe make you feel small, or does it make you feel special? I genuinely want to know. And while you're at it, if this video is giving you something, if it is making you think, making you wonder, making you feel something, hit that like button and share this with someone who would appreciate it. These are the kinds of conversations that matter, and I want to have them with as many people as possible. Now, I want to take a detour into what is arguably the most unsettling aspect of cosmic darkness, something that makes the darkness of space seem almost cozy by comparison. I want to talk about dark matter and dark energy. Because the darkness of space is not just about the absence of visible light, it is about the very composition of the universe itself. And what we have discovered about that composition is frankly humbling to the point of being embarrassing. Here is the situation. We have spent centuries studying the universe. We have built telescopes that can see billions of light years into space. We have constructed particle accelerators that can probe the fundamental building blocks of matter. We have developed mathematical theories of extraordinary precision and beauty. And after all of that effort, all of that ingenuity, all of that collective human brilliance, we have come to a startling conclusion. We have no idea what 95% of the universe is made of. 5% of the universe consists of ordinary matter, the stuff we are familiar with, the atoms that make up stars, planets, gas, dust, and people. Protons, neutrons, electrons, combined in various ways to form the elements of the periodic table. This is the stuff of chemistry, biology, everyday life, and it constitutes a mere 5% of the total mass energy content of the cosmos. 27% of the universe is dark matter. We know it exists because we can see its gravitational effects. Galaxies rotate faster than they should if they contained only the matter we can see. Galaxy clusters are more massive than the visible matter within them can account for. The cosmic web of large-scale structure is shaped by the gravitational influence of enormous amounts of unseen mass. The CMB fluctuations are consistent with a universe containing far more matter than we can detect with our telescopes. All of these observations point to the same conclusion. There is a vast amount of matter in the universe that does not emit, absorb, or reflect light. It does not interact with the electromagnetic force at all. It interacts with ordinary matter only through gravity. It is, in the most literal sense, dark. The story of dark matter's discovery is a fascinating one, and it begins with a Swiss astronomer named Fritz Zwicky. In 1933, Zwicky was studying the Coma Cluster, a large cluster of galaxies about 300 million light-years away. By measuring the speeds at which the galaxies within the cluster were moving, Zwicky calculated the total mass of the cluster needed to gravitationally bind it, to keep the galaxies from flying apart. He then compared this gravitational mass with the mass he could account for by adding up the light from all the visible galaxies. The gravitational mass was about 400 times larger than the visible mass. The cluster was far more massive than it appeared. Zwicky proposed that the cluster must contain a large amount of unseen matter, which he called Dunkelmaterie in German, dark matter. His proposal was largely ignored at the time. The observations were difficult and the uncertainties large, and most astronomers were not prepared to accept such a radical claim. It wasn't until the 1970s that dark matter became impossible to ignore, thanks largely to the work of an American astronomer named Vera Rubin. Rubin studied the rotation curves of spiral galaxies, the relationship between the orbital speed of stars in a galaxy and their distance from the galaxy's center. According to Newton's law of gravity, stars farther from the center of a galaxy should orbit more slowly than stars closer to the center, just as planets farther from the sun orbit more slowly than planets closer to the sun. This is because the gravitational pull weakens with distance. If most of a galaxy's mass is concentrated in its central region, where most of the visible light is concentrated, then the orbital speed should decrease with distance from the center. But that is not what Rubin found. In galaxy after galaxy, she measured rotation curves that were flat, meaning the orbital speed of stars remained roughly constant even at large distances from the center, far beyond the visible extent of the galaxy. This was impossible if the visible matter was the only matter present. The only explanation was that each galaxy was embedded in a vast halo of invisible matter, extending far beyond the visible disk, providing the additional gravitational pull needed to keep the outer stars orbiting at such high speeds. This invisible halo had to contain far more mass than the visible galaxy itself. Rubin had provided the most compelling evidence yet for the existence of dark matter. Since Rubin's work, the evidence for dark matter has become overwhelming. It comes from multiple independent lines of observation, galaxy rotation curves, the mass of galaxy clusters as measured by gravitational lensing, the pattern of fluctuations in the CMB, the large-scale distribution of galaxies in the cosmic web, the observed abundances of light elements produced in Big Bang nucleosynthesis. All of these observations are consistent with a universe containing about 5 times as much dark matter as ordinary matter. The existence of dark matter is not in question. What is in question is what dark matter actually is. The leading candidates for dark matter particles are weakly interacting massive particles, or WIMPs. These are hypothetical particles that have mass and therefore interact gravitationally, but do not interact with the electromagnetic force and therefore cannot be seen. WIMPs are predicted by several extensions of the standard model of particle physics, most notably supersymmetry. If WIMPs exist, they should occasionally interact with ordinary matter through the weak nuclear force, producing faint, rare signals that might be detectable in extremely sensitive experiments. Over the past several decades, numerous experiments have searched for WIMP dark matter using different techniques. Some have placed detectors deep underground to shield them from cosmic rays, hoping to catch the rare interaction of a WIMP with an atomic nucleus. Others have searched for the annihilation products of WIMPs in space, looking for excess gamma rays or positrons that might signal dark matter particles colliding and destroying each other. Still, others have attempted to produce dark matter particles directly in particle accelerator experiments at CERN's Large Hadron Collider. So far, none of these searches have produced a confirmed detection. The dark matter particle, whatever it is, remains stubbornly invisible, stubbornly undetected, stubbornly dark. Other candidates have been proposed. Axions are hypothetical very light particles originally proposed to solve a problem in quantum chromodynamics, the theory of the strong nuclear force. If axions exist, they could be produced in enormous quantities in the early universe and could constitute the dark matter. Experiments like ADMX, the Axion dark matter experiment, are searching for axion dark matter by looking for the conversion of axions into detectable photons in the presence of a strong magnetic field. Sterile neutrinos, a hypothetical heavier cousin of the known neutrinos, are another candidate. And primordial black holes formed not from stellar collapse, but from density fluctuations in the very early universe, have been proposed as a non-particle candidate for dark matter, though observational constraints make it unlikely that they can account for all of it. The mystery of dark matter is profound. Here is something that makes up 27% of the universe, something that shapes the structure of galaxies and the cosmic web, something that surrounds us at this very moment. There are estimated to be millions of dark matter particles passing through your body every second. And yet, we cannot see them, cannot detect them directly, cannot identify them. We know they are there because we can see their gravitational effects, like seeing the footprints of an invisible giant in the snow. But the giant itself remains unseen. The darkness of dark matter is not the darkness of empty space. It is the darkness of a universe that contains more than we can perceive, more than we can detect, more than we can understand. It is humbling in a way that is hard to overstate. And then there is dark energy, which is even more mysterious, even more humbling, even more disturbing. At least with dark matter, we have a clear observational signature, gravitational effects that tell us roughly how much there is and where it is. With dark energy, we know even less. We know that it is causing the expansion of the universe to accelerate. We know that it makes up about 68% of the total energy content of the universe. We know that its energy density appears to be roughly constant over time, meaning that as space expands, new dark energy appears to fill the new space, maintaining a constant density throughout the universe. This is utterly unlike any form of matter or radiation, whose density decreases as space expands. Dark energy is not diluted by expansion. It is, in some sense, a property of space itself, an intrinsic energy associated with every cubic centimetre of the vacuum. The most straightforward theoretical candidate for dark energy is the cosmological constant, originally introduced by Albert Einstein in 1917, and then famously retracted by him as his greatest blunder. Einstein introduced the cosmological constant as a mathematical term in his equations of general relativity that would balance the gravitational attraction of matter and produce a static, unchanging universe, which was the prevailing assumption at the time. When Hubble discovered that the universe was expanding, the cosmological constant seemed unnecessary, and Einstein abandoned it. But the discovery of accelerating expansion in 1998 brought it back. If the cosmological constant is the correct explanation for dark energy, then it represents the energy of empty space itself, the vacuum energy predicted by quantum field theory. The problem is that when physicists attempt to calculate the vacuum energy using quantum field theory, the result is either 0 or a number that is roughly 10 to the 120th power times larger than the observed value of dark energy. That is a discrepancy of 120 orders of magnitude, which is, without exaggeration, the worst prediction in the history of physics. This is known as the cosmological constant problem, and it is one of the deepest unsolved problems in theoretical physics. Either our understanding of quantum field theory is fundamentally wrong, or there is some unknown mechanism that cancels out almost all of the vacuum energy, leaving behind the tiny residual that we observe as dark energy. Neither option is satisfying. So here we are. 95% of the universe is made of stuff we don't understand. 27% is dark matter, particles or entities that we can detect only through gravity and that have eluded every direct detection experiment. 68% is dark energy, a force or property of space that is accelerating cosmic expansion and that we cannot explain even in principle. The universe is not just physically dark, in the sense of being mostly devoid of visible light. It is conceptually dark, in the sense that most of it is a mystery. We are like people living in a vast mansion, able to see and understand only a few rooms, while the rest of the house is shrouded in impenetrable darkness. We know the other rooms exist because we can hear sounds coming from them, feel vibrations through the walls, but we cannot open the doors. We cannot turn on the lights. The darkness is not just out there, in the voids between galaxies. It is in here, in our understanding, in our theories, in the gap between what the universe is and what we know about the universe. This might sound discouraging, but I actually find it exhilarating. Think about it. We live in an era when 95% of the universe remains to be discovered. The greatest discoveries in physics are not behind us. They are ahead of us. Whoever figures out what dark matter is, whoever cracks the mystery of dark energy, whoever develops the theory that explains why the vacuum energy is so small, they will have made discoveries that rank alongside Newton's law of gravity, Einstein's general relativity, and the development of quantum mechanics. The darkness of our ignorance is not a dead end. It is an invitation. It is the universe saying, there is so much more here, so much more than you have found so far, and the journey of discovery has barely begun. Now I want to take us to the absolute extreme of cosmic darkness, to objects that embody darkness so completely that they have become synonymous with it. I want to talk more deeply about black holes. Because black holes are not just dark objects in space. They are the places where our understanding of darkness, of physics, of reality itself reaches its limit and breaks down. We discussed black holes briefly earlier, but now I want to go deeper. A black hole is formed when a massive star, typically more than about 20 to 25 times the mass of our Sun, exhausts its nuclear fuel and can no longer support itself against the crushing force of its own gravity. The core of the star collapses, and if the core mass exceeds about 3 solar masses, no known force can stop the collapse. The core shrinks past the point where it would become a neutron star and continues to shrink without limit, at least as far as our current physics can predict. The result is a singularity, a point of infinite density and infinitesimal size, surrounded by an event horizon, a spherical boundary in spacetime from within which nothing can escape. The event horizon is not a physical surface. You cannot touch it, stand on it, or bounce off it. It is a mathematical boundary, a surface defined by the geometry of spacetime itself, the boundary between the region of spacetime from which light can escape and the region from which it cannot. Once something crosses the event horizon, it is gone from the observable universe. No signal, no light, no information of any kind can travel from the inside of the event horizon to the outside. The event horizon is, in the most precise physical sense, the boundary of absolute darkness. And now let me tell you about the image that I think is one of the most important photographs ever taken. On April 10, 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole, specifically the supermassive black hole at the center of the galaxy Messier 87, a giant elliptical galaxy about 55 million light-years away. The image showed a bright ring of superheated gas swirling around a dark central region, the shadow of the black hole's event horizon. The dark region was not literally the event horizon, but rather the area from which no light could reach us, because it had been captured by the black hole's gravity. It was a photograph of darkness, of the absence of light, of the gravitational prison that is the defining characteristic of a black hole. In May 2022, the same team released an image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy, about 27,000 light-years away, with a mass of about 4 million solar masses. Again, the image showed a bright ring surrounding a dark center. These images are striking not for what they show, but for what they don't show. The dark center is not merely a shadow. It is a region of space-time from which no information can reach us. It is, quite literally, a hole in our ability to know the universe, a permanent blind spot in our cosmic vision. The darkness at the center of those images is not ordinary darkness. It is the darkness of fundamental physical law, the darkness that the universe's own geometry imposes on our ability to see and know. Inside the event horizon, our physics tells us that space-time is so severely warped that the roles of space and time are, in a sense, exchanged. Outside the event horizon, you can move freely in space but are compelled to move forward in time. Inside the event horizon, you are compelled to move inward in space, toward the singularity, just as surely as you are compelled to move forward in time outside. Reaching the singularity is not a matter of where you go, it is a matter of when you arrive. The singularity is in your future, and nothing can change that, just as nothing can prevent tomorrow from coming. This is a darkness that is woven into the fabric of space-time itself. It is not the darkness of absence, it is the darkness of inevitability. And at the singularity, or whatever replaces it in a more complete theory, all our understanding ends. General relativity predicts that the density becomes infinite, that space-time curvature becomes infinite, that the very concepts of space and time cease to have meaning. This is almost certainly not what actually happens. Infinities in physics usually signal not a real physical state, but the breakdown of the theory being used. Just as the classical theory of electrodynamics produces infinities when applied to the electron, infinities that are resolved by quantum electrodynamics, the infinities of general relativity's singularity will almost certainly be resolved by a quantum theory of gravity. But we don't have that theory yet. String theory, loop quantum gravity, and other approaches to quantum gravity are still works in progress, and none has yet made a testable prediction about the interior of a black hole. The singularity remains hidden behind the event horizon, protected from our observation by the cosmic censorship conjecture, which states roughly that nature conceals its singularities behind event horizons so that they can never be directly observed. The deepest darkness in the universe is also the most well-guarded, but Stephen Hawking's discovery of Hawking radiation adds a layer of paradox and mystery to black holes that makes them even more fascinating. If black holes evaporate over time by emitting Hawking radiation, then eventually all the mass and energy that fell into the black hole will be returned to the universe as thermal radiation. This seems fine at first, just a very slow process of converting concentrated mass energy into dispersed radiation. But there is a problem. Hawking radiation is thermal, meaning it carries no information about what fell into the black hole. It is like the heat radiating from a fire. You can tell the fire is hot, but you cannot tell from the heat alone whether the fire is burning wood, paper, or diamonds. The information about what was burned seems to be destroyed, but this violates a fundamental principle of quantum mechanics, which states that information cannot be destroyed. In quantum mechanics, the evolution of a system is unitary, meaning that if you know the state of the system at any time, you can in principle calculate its state at any other time, past or future. Information is never lost. But if a black hole absorbs information and then evaporates into featureless thermal radiation, the information has been lost. This is the black hole information paradox, and it has been one of the central problems in theoretical physics for nearly 50 years. Various proposed solutions have been offered. Perhaps the information is encoded in subtle correlations in the Hawking radiation that are undetectable in practice, but preserve unitarity in principle. Perhaps the information is stored at the event horizon in a thin shell of high-energy particles, the so-called firewall, that an infalling observer would encounter at the horizon. Perhaps the interior of the black hole is connected to the exterior through Einstein-Rosen bridges, wormholes, in a way that preserves information through the relationship between entanglement and space-time geometry, the ER equals EPRA conjecture, proposed by Juan Maldacena and Leonard Susskind. Perhaps the information is stored holographically on the event horizon, in a way consistent with the holographic principle, which suggests that all the information contained within a volume of space can be described by a theory on the boundary of that volume. Each of these proposals has supporters and detractors, and none has been conclusively proven or disproven. The information paradox remains open, a reminder that the deepest darkness in the universe harbours the deepest mysteries. There is something that I find deeply compelling about the relationship between darkness and knowledge that runs through all of this. At every scale, from the darkness of a molecular cloud to the darkness of a cosmic void to the darkness inside a black hole, we find that darkness is not just the absence of light. It is the presence of mystery, the existence of things we do not and perhaps cannot understand. The darkness of space is a physical darkness, a literal lack of photons. The darkness of dark matter is a particle physics darkness, an inability to identify the substance that shapes the structure of galaxies. The darkness of dark energy is a cosmological darkness, an inability to explain the force that dominates the universe. The darkness inside a black hole is a theoretical darkness, a failure of our best physical theories to describe what happens there. And the darkness of the far future is an existential darkness, the universe's inexorable march toward a state in which no knowledge, no complexity, no consciousness is possible. These are all different kinds of darkness, but they are all facets of the same fundamental truth: the universe is mostly unknown to us, and much of it may be forever unknowable. The darkness is not just around us, it is within our understanding. And yet, and I cannot stress this enough, look at what we have done. Look at what this small, fragile, mortal species on this small, fragile, mortal planet has accomplished. We figured out why the sky is dark at night, and in doing so, we discovered that the universe had a beginning and is expanding. We detected the afterglow of the Big Bang, a whisper of light from 13.8 billion years ago, and used it to determine the age, composition, and geometry of the universe. We discovered that most of the universe is invisible, made of dark matter and dark energy that we cannot see or touch, and we did this not by seeing these things, but by meticulously measuring their indirect effects. We took a photograph of a black hole, an object defined by the inability to photograph it, by linking radio telescopes across the entire planet into a virtual telescope the size of Earth. We sent spacecraft beyond the orbit of Pluto and used them to measure the faint background glow of the cosmos itself. We built mathematical models that can predict the future of the universe for trillions of years and beyond. We did all of this from a small rocky planet, using the 3 pounds of neural tissue between our ears and the tools we fashioned with our hands. The darkness of the universe is vast and deep, but the light of human understanding is real, and it is growing. I want to pivot now to something more personal, more immediate, something that connects the grand cosmic narrative to your everyday life. I want to talk about light pollution and what it means for our relationship with the darkness of space, because there is a profound irony in our situation. We have spent this entire video discussing how dark space is, how the voids between galaxies are some of the emptiest, darkest places in existence, how the future of the universe is one of ever-deepening darkness. And yet, most people living on Earth today cannot even see the stars. The darkness that was once our window into the cosmos has been obliterated by the artificial light of our civilization, and we are losing something precious in the process. Light pollution is the brightening of the night sky caused by artificial light sources, streetlights, buildings, billboards, vehicles, and the general glow of urban and suburban areas. It is one of the most pervasive and least recognized forms of environmental pollution on the planet. According to a study published in Science Advances in 2016, 80% of the world's population and more than 99% of the population of the United States and Europe live under light-polluted skies. 1/3 of the world's population cannot see the Milky Way, our own galaxy, with their naked eyes. In many major cities, the number of stars visible on a clear night has dropped from several thousand to a few dozen or even fewer. The night sky that inspired Newton, Galileo, Kepler, and every ancient civilization on Earth has been effectively erased for most of humanity.